Okay, in this video we are going to talk about finding the volume of revolution for a region revolved around something that is not an x or y axis, so something a little bit different. So we'll start off with this example that we have right here. Our goal is to find the volume of the solid that is generated by the region in the first quadrant, bounded by y equals x squared, the x-axis, and x equals 2, revolved about the line x equals -4. So the first thing, just like for all of these types of problems, that we want to do is make a quick sketch of the graph so we can visualize what it is that's going on. So the first thing I'm going to graph is y equals x squared. And because this problem says we're only going to worry about the region in the first quadrant, I'm only going to graph it in the first quadrant. We're also going to worry about the x-axis, which we already have here, but I'll just highlight that so we don't lose it. And then we are going to graph x equals 2. So x equals 2 is this straight line right here, vertical line, x equals 2. So then we can see what our region is. It looks like this right here is our region in question. And now what we want to do is we want to think about what it is that we are going to revolve this about. So it looks as if we are going to try to revolve this about the line x equals -4. So what it is I'm going to revolve around, I'm actually going to draw that in a dotted line so we can realize that that is not part of our bound. It's not part of our region. So this is the line of revolution. So if you can see, this is almost like revolving this around the y-axis, only what's happened is it's shifted over, which means we are going to want to try to visualize this almost like you're tilting your head, if you will, to think about which function is on top and bottom. So because we are revolving around something that is like the y-axis, we are now going to want to do an integration with respect to y rather than with respect to x. Anytime you're revolving around something that's like the y-axis, we're going to do an integration with respect to y, which means I should rewrite each of these equations so that I have an x equals. So in this case, I'll have an x equals the square root of y. I already have the other function written as an x equals, so that takes care of that. And then what we're going to do is I'm going to look at this sliver that I have right here in order to think about the top and bottom, or the outside radius and the inside radius, when we do a washer method. So this one is going to be a washer method. Let's go through and set up this volume. My volume is going to be washer method has a pi times the integral. Remember, what we really need is we need a big radius squared minus a small radius squared. So I'm gonna write that down just to help us visualize what's going on here. This intersection point, it looks like right here, is going to have when x is equal to 2, y is going to be 4. So that takes care of our bounds. So I'll have pi is going to go pi times the integral from 0 to 4, because remember, we are revolving around something like the y-axis, so I'm integrating with respect to y. So those are y bounds that I have. And then I want to think about my big radius and small radius. Now you can think about that this blue line, that x equals 2, is going to be on the outside that entire time when I revolve it way over here. So we want to think about what that radius is going to be after I revolve it way to the other side. The radius is always going to be from your function to whatever it is you're revolving around. So in this case, my function was x equals to 2, and I'm revolving around x equals to -4. So the radius is always going to be that distance, and it looks like that distance is going to be 2 units is going to get me to the origin, and then I have to do an extra 4 units to get all the way to what I'm revolving around. So my outside radius is going to be 2 minus the -4, which just does turn into a 6. Those negatives really will cancel. Okay, let's do the same thing for the inside radius, the smaller radius. So in this case, it looks like the red function is going to be on the inside when I do this revolution. Your radius is always going to be from your function to whatever it is I'm revolving about. So from my function to whatever it is I'm revolving about. So in this case, I'm revolving around the x equals 4. My function was x equals the square root of y, and the distance between them will become square root of y is going to give me that distance right there. So square root of y will give me this distance, and then an extra 4, so that's why it's a +4. These two negatives really will turn into a +4. All right? Excellent. Let's continue on to try to find that volume. Now this is going to become pi times the integral from 0 to 4. Looks like I'll have 6 squared, which is 36, minus Oh, that was a small radius squared, sorry. And I'm going to rewrite this as the square root of y plus 4, and then square root of y plus 4 squared becomes the square root of y plus 4 times the square root of y plus 4. I'm just going to write that out twice so I can go ahead and work through the algebra for this now. Now that will become pi times the integral from 0 to 4 of 36 minus, when I start to do the distribution, or the FOIL, whichever way term you're used to, root y times root y is going to give me y. And then I will get 4 root y plus another 4 root y plus 4 times 4, which is 16. Still have the dy. I'll continue the algebra here. Pi times the integral from 0 to 4. Now I'm going to have, sorry about that, 36 minus y minus 8 root y minus 16 dy. Then this is going to become pi times the integral from 0 to 4, 20 minus y minus 8y to the 1/2, which is root y dy. That 20 came from the 36 minus 16. Okay, so now we integrate. So now I'm going to go through and do this integration. We'll go ahead and see if I can shift that up a little bit here. So now when I do this integration here, I will end up with pi times 20y minus y squared over 2 minus 8y to the 3/2 times 2/3, and that was adding 1 to the power and dividing by the new power. Evaluated from 0 to 4. All right, that's going to be evaluated from 0 to 4. Sorry about that. Okay, so let's shift that up one more time, just a little bit, so I can have space. All right, then this is going to be pi times, plug in 4, that will give me an 80, minus 16 divided by 2, which is 8, minus, this will become a 16/3, and the 16/3 came from 8 times 2/3, and then when I plug in the 4, I'll just write that out as 4 to the 3/2. Now plugging in the lower bound of 0 happened to give me 0 everywhere, so that will just be a minus 0. Then we just have to combine our like terms to get our final answer of 88 pi thirds. And again, this is units cubed because we found the volume. Ta-da! All right, so that's a good problem. What we did there is we used the washer method to do a volume of revolution where a region is revolved around something that is like the y-axis but just shifted over. So that shifting over still meant it was like the y-axis, so I still had to do the dy. I just had to add in that extra 4 units of space for each of the 2 radii. All right, let's do another example. Let's do one more example, same type of problem, just a different volume, okay? So the next example I'm going to work with here is going to be finding the volume of a solid generated when the region R is going to now be in the 4th quadrant, bounded by the graphs of y equals, looks like negative x squared over 16, and y equals negative 1, and x equals 0, revolved about the line y equals 1. So let's go through and do this same process. The first thing that we want to do is make a sketch of the graph. So I'll graph each one of them. Y equals negative x squared over 16. That's that upside down parabola. That over 16 just means this is stretched slightly different, but the graph doesn't have to be to scale, so that's sufficient. And then y equals negative 1. It looks like is this horizontal line. Here's my y equals negative 1. And x equals 0 is, in fact, the y-axis. And this problem also only cared about the region in the 4th quadrant. So this is that region that is bounded in the 4th quadrant by those 3 equations. Okay, so then the next step is to figure out what I'm revolving about. In this case, it looks like I'm trying to revolve around the line y equals 1. So whatever it is I'm revolving around, I'm going to draw that again as a dotted line just to not overcomplicate it. And that's what we're going to revolve things around. Now that I know what I'm going to revolve around, you can decide whether you're going to use an integration with respect to x or with respect to y, so a dx or a dy. It looks like this is revolving around something that is like the x-axis. It just happens to be shifted a little bit. But because it's just like the x-axis, we are going to do an integration with respect to x. So let's go ahead and do this volume. So this one I really don't have to tilt my head to think about which one's maybe on top and bottom or on the outside versus the inside. All right, let's go ahead and make sure we find this intersection point. So in order to find that intersection point, sometimes it's a little bit more obvious than others. That first example was maybe a little bit easier. This one, maybe it's not quite as obvious, so I'm actually going to just set those two equal to each other and do the algebra. I can multiply both sides by negative 16, and then I can take the square root of both sides, and that's where I'm going to get that this intersection point turned out to be a positive 4. All right, so let's go ahead and work through this one, again using the washer method. So this is the same method here. I am going to do my pi times the integral. This one's going to have a dx. Again, I'm integrating with respect to x because I'm revolving around something that is like the x-axis. And then one more time, we really want to think about a bigger radius squared minus a smaller radius squared. Okay, that's what we're really thinking about for these problems here. So if you're thinking about the bigger radius in this problem, it looks like if I were to take this sliver that I have, that I've drawn right here, and try to revolve that around the line y equals negative 1, so it's sort of popping out of the screen at you and it's creating a washer. It looks like the blue line is going to be on the outside that entire time, and then that red graph will be on the inside the entire time. So because the blue graph is going to be on the outside, that's going to be the bigger radius. So the radius is always going to be the distance from your function to wherever it is you're revolving about. And in this case, the distance that I'm thinking about, and let's rewrite this over here, is going to be my function was y equals negative 1 to the y equals 1. So that distance, you always think about it in terms of whatever your function is minus whatever number it is you're revolving about. Okay, whatever your function it is minus whatever it is you're revolving about. Okay, and then that's going to, which of course that distance is 2. It happened to be negative 2, but when you square it, that's going to go away anyways, so that's not really that big of a deal. Okay, minus. Now let's do the same thing with the inside radius. It looks like the red function here is the inside radius. So again, the distance, or your radius, is always going to be the distance from the function to whatever it is I'm revolving about. So that distance is going to be my function, which is negative x squared over 16, minus whatever it is I'm revolving it about. So that's my big radius squared minus my little radius squared. And then the bounds here, it looks like went from x equals 0 to x equals 4. So those bounds will be from 0 to 4. All right, so that's the setup. Now we have to go through and integrate. So this will become pi times the integral from 0 to 4. This will become negative 2 squared, which becomes a positive 4 minus. This next one, again, it's maybe a little bit trickier to do it in your head, so it's easier to just write it out twice and then actually do the foiling. So we'll do that. This is going to be pi times the integral from 0 to 4 of 4 minus, and when I start to distribute or FOIL, however it is that you think of that, x squared over 16, sorry, negative x squared over 16 times negative x squared over 16 will become a positive x to the 4th, and then 16 times 16. And then we're going to do the same thing when we start to distribute the rest of them. So it'll be plus x squared over 16 plus x squared over 16. Those pluses happened again because the negatives canceled, and then plus 1 dx. Okay, and then we're going to go ahead and just combine like terms completely, and then we'll integrate. So we'll go ahead and we'll make that 4 minus x to the 4th over 256 minus, and that'll become an x squared over 8 minus 1 dx. I've distributed some negatives and combined like terms along the way. Then I'll have pi times the integral from 0 to 4 of 3 minus x to the 4th over 256 minus x squared over 8 dx, and then we can integrate. So pi times 3x minus, now that you can think of that as like a 1 over 256, and then that's an x to the 5th over 5th when I integrate minus, and again you can think of that as like a 1/8, and then an x cubed over 3 when I integrate. Evaluate that from 0 to 4. We'll go ahead and plug in 4, and when you plug in 4, I'm going to get 3 times 4 here, 4 to the 5th over 5. So the numbers get a little bit big, but we can plug in 4 and combine all of our like terms. So when we plug in our 4 and combine our like terms, we're going to end up with 128 over 15 units cubed. All right, so that's the volume of that region. So those are a couple of examples of how to do a volume of revolution using the washer method, but revolved around something that's not an axis, not the x-axis or the y-axis. One of the main things, just as a summary, that you want to keep in mind is when you're revolving around something that is like an x-axis and you're doing the washer method, you're going to use a dx. And when you're revolving around something that is like, I didn't mean to mess that up. If you're revolving around something that is like a y-axis and you're doing the washer method, then you're going to do a dy. That's the main thing to keep in mind to help keep track of your integration. Ta-da!